Hello, welcome to our presentation about our SCARA arm robot. We built a robot, a two-axis robotic arm, to draw lines, squares, and triangles. My name is Yakovich, and the rest of my group partners are Cade, Tillema, Taylor Sisneros, and Joseph Conrow. First, I will be describing the engineering requirements we had to meet. The first, the system must draw faster than 4 inches per second. The second, it must draw a 10-inch straight line. The third, it will use SCARA topology. The fourth, the controlling commands will be inputted as G-code commands. The fifth, upon receiving an M6 command, the machine operator must mount a crayon, pen, or pencil. The sixth and seventh were the ones that we implemented additionally. And the sixth is upon receiving G-code coordinates from the Python GUI, the coordinates will also be displayed on an e-ink display. The seventh is that the robotic arm must be able to draw a triangle and quadrilateral.
Hello, my name is Taylor Sisneros, and my primary job on the robot was to work with the Python GUI and to begin implementation of the G-code. I used a simple program called NC Viewer to simulate the G-code commands and what it might draw. So this first video shows the horizontal line and the two commands that are simply used, and you could see that it moves 10 units in the X direction. My next simulation is the vertical line test, and the G-code is pretty much the same except it goes in the Y direction this time. And as you can see, the plotted line, and then also you could see the Y going up 10 units. Next two implementations were the square and the triangle. So starting off with the square, you can see it drawn right there. These are the five different commands that are used for the square. And as I move through, you can see the x-axis going up 5 units, then going to the y-axis 5 units, going back down the x-axis 5 units, then back to the origin to complete the drawing of the square. And then right here I just showed the coordinates again. The final implementation of the G-code was the triangle. This only took about 4 commands, and as you can see, there's the drawing of the triangle. Here's me running through the different commands, going 5 units up, 5 units to the Y direction, and then back to the origin to create a simple square. With these G-code commands, I then needed to implement them into the Python GUI. This first slide just shows the different libraries and also me creating the canvas window. So the tkinter library is used for the actual window pop-up of the Python GUI, and the serial library is used for the e-ink serial communication. And as you can see with root.title, I create the canvas with the title Robot Arm GUI. I make it 500 by 300 units, and I also make 3 different global variables to keep track of the canvas, the X coordinate, the Y coordinate, and then at the bottom you could see the 2 different serial commands that are needed to communicate with the e-ink display. This next slide shows the beginning operation and horizontal line functions. With the begin operation function, you can see it simply sets the robot with Arduino 2.write to the origin position, and it also creates the text and the colors for the Python GUI window. This one's pretty simple, so there's not much to it. Below that, you can see the horizontal line function, and this time I set the coordinate, the X coordinate plus 10, and as you can see with the Arduino 2.write, we write G1 X10 to be able to move 10 units in the X direction and draw a horizontal line. You can also see that we implement the canvas tracker to keep and delete it as well to delete the line if need be. And then I also update the coordinates on the Python GUI as well. This next two functions are my vertical line functions and then the reset function. The vertical line is almost exactly the same as the horizontal line function, except we increase the y coordinate by 10 units and then move 10 units and then send a G-code command that moves 10 units in the y direction. Also, as you can see with the Arduino 2.write line, that we set the speed to approximately 4 inches per second on the robot with the F240 command. Then we have our reset command, which is to simply reset the robot back to its origin position and to make sure that if there's any garbage data sent to the robot, that this resets the origin and makes it so we can draw any other shape we want. And all this simply does is write all zeros to the speed as well as the x and y coordinate with the Arduino 2.write. The next couple functions are the functions implemented for the square. So this function at the top is the first square function, which moves 10 units in the x direction. But as you can see at the bottom, I also have 3 different commands that route my 3 other square functions to be able to draw simultaneously after the other. So this one, like I said, simply moves the robot 10 units in the x direction to start the square. Then, as you can see in my square 1 function, I then write 10 units to the y direction, and the root dot after 4000 square 1 in my first function, it allows the square after it goes 10 units in the x direction to go then 10 units in the y direction. My next 2 functions are also the square functions, and my square 2 function allows to return back to the 0 position of the x coordinate, but keep the y coordinate at 10 units. So this creates the third side of the square. And then finally, my square 3 function completes the square by having the robot return to the origin that it originally started at. My next couple functions implement the triangle drawing. So this simply, the first one, simply adds 10 units to the x direction. And then as you can see, the root dot after functions at the bottom routes my triangle 1 and triangle 2 function to this function to be able to draw the whole shape. If you look at the triangle 1 function, I move 10 units to the y direction and keep the x coordinate the same. And then if you go to the next slide, the triangle 2 function on this slide returns to the origin, and that would complete a full square or full triangle drawing. And as you can see, I subtract x and y, or 10 units from the x and y coordinates. And then also, I'm also updating these coordinates all on the GUI, which we will see in a video in just a minute. After I create the canvas object, I also allow this canvas.pack function to be able to add text to the canvas. And then these next few functions are used to create the different buttons that you will see in the video coming up. Also the positions of those buttons are set below with those different coordinates. And then the final line of code with the Python GUI is a root.main loop, which routes the whole function back to the beginning to be able to work completely. Right here is a video of the Python GUI implementation, and this was the first implementation. So you could see at the beginning, we start by beginning operation, then we could add horizontal lines, reset the coordinates. Right here, you will see the square being drawn, 10 units in the x direction, 10 units in the y, returning back to the 0 position of the x coordinate, and then returning back to the origin. Here you could see that we can draw a triangle right from that by adding to the y direction, adding 10 to the x direction, then again returning to the origin, and that is it for the Python GUI implementation.
My name is Yakovich again, and I will be explaining the e-ink display code. First, I used the WaveShare 2.9-inch e-ink display library. This is an online library free to use for anybody who buys one of their products. This gave me the bulk of the functions to be able to display whatever I needed to on the e-ink, and it can be found online at the first link. The second link is to my GitHub that shows all of the code, but I will also be explaining that here. So to begin, we set up, we pretty much just set up the code, set up our serial communication with the Python GUI implemented by Taylor. The image, the unsigned char image, is simply just a white image, so nothing gets in the way. And I also set to where it's going to be on the e-ink. The void setup sets up the serial. Then we move to our loop, which is the most important part. To begin, just create a serial string. If there's communication in the serial port, read the string in, and copy it to a char array, because the e-ink display functions only work with char array strings instead of regular strings. So once that has happened, once we've actually received input from the Python GUI, I run a while loop. So this while loop sets where I want to place the string on the e-ink with those first 4 lines of code. Then it actually draws the string with those next 3 lines of code. And finally, the if statement here really just checks to see if there's new input coming in. If there's new input and we need to update the e-ink display, it will clear the string array that we were using, and it will break the while loop to return to where we were before to get the input and begin it all over again. There's also a simple delay in here to ensure that no data from the new string is placed in the old one. And here's the video of it working in tandem with the Python GUI. As you can see, a button will be clicked on the Python GUI and the coordinates will update on the e-ink display. The e-ink display is hooked up to the Arduino where the code is written. And you can see that the Arduino is just hooked up through the USB port connected to the Python GUI. Here we do the square, which will update it in real time as the robot is moving. You can see works the exact same way as Taylor's Python GUI, but just displays the coordinates on the e-ink instead, so the user can have a clear understanding of where exactly the robot arm is at the specific moment. And then finally, here's the triangle. And you see it returns the origin, just how it did in the Python GUI, and works the same with the G-code. That's all I have for the e-ink, and thank you for your time.
Hello, my name is Joseph Conrow, and I did the physical structure of the robot as well as the implementation of the G-code interpreter that drew the actual output of the drawings from the robot. Here is the prototyping of my design, my physical design. My prototype on the right, this is the initial, with not all the parts put together yet, but just a layout of generally what we were planning on doing, not the exact dimensions. I had some spare acrylic that I laid around that I used to prototype. You can see on the left links to certain websites that I was particularly inspired by. I did do lots of research online to find what parts and layouts people used to have a SCARA topology structure of a robot. And here is the SVG file layout that I had for TechBot's laser cut order I made. And I was able to get thicker acrylic to provide rigidity to the robot and make it more reliable. And precise cuts were allowed. On the left are the 2 arms, and the right was the top of the base. And these different rings were used for just in case, didn't use them, but just in case we needed extra spacing or spacers or whatnot. Here are the actual dimensions of the different thicknesses and widths between each of the cuts and the height of the robot's actual arm. And here is what I worked on with Nick. We had an initial clamp to use the tooling, but the tooling was not secure. The clamp was not as strong as we intended, and therefore we found a better wedge method for the tape that used friction to resist the tools from falling out. And it was easy to switch out as well. You just jam it in there and you pull it out. Very quick and very easy and very reliable and stable. Here is the actual final layout of the different shafts in the 20-tooth and 60-tooth gears that were connected tightly with the 400mm and 200mm pulley system. And here's the bottom that we use rubber stickers on. That way you kept it from sliding when drawing. And the bottom you can see also fit both Arduinos and the E-Ink Arduino as well as the G-code interpreter Arduino with the drivers on top with the PCB shield. And you can see it connects through both COM buses on the right side, bottom right, as well as the 20-volt power supply. And here's the movement I made for the robot. We used inverse kinematics instead of using the angles to find the Cartesian coordinate. We used the Cartesian coordinate to find the angles. These angles were translated to each motor's movements. That way we can know what position the motor must be in to find and achieve a certain Cartesian coordinate. Here is the library that we initially used. This is iteration 1. It was the GRBL library, open source. They used for CNC, X and Y, Cartesian coordinate implementation. However, ours is polar. SCARA topology uses polar coordinates. So I did also find a GRBL extension that was pertained to using inverse kinematics to translate the SCARA topology into the Cartesian coordinate output of the GRBL software. Here is the actual implementation and the drawings that the GRBL was able to use. It wasn't perfect. We did some debugging and ended up drawing pretty good words from our GRBL G-code sender program that you can see on the left. It sends the G-code through the bus. Here's the actual robot working. You can see it's very precise, very smooth. However, it ended up not prevailing and being reliable enough to use on final day. So, here is what happened the week of the due date. I accidentally plugged a 20-volt power supply into the Arduino, which receives, it's supposed to receive 5-volt, fried the Arduino, and inadvertently fried the drivers for the motors. We debugged and troubleshooted it for a couple days, and I wasn't able to find out what the problem was. We ordered new parts and drivers, and that way we were able to test once again. And it was the day before, and the GRBL was just not responding properly and not as expected. So that night I wrote the rendition code. So here is what I had for scratch paper and my initial thoughts and plans. And you can see we still use inverse kinematics as well. Nothing changed there, but the implementation of how it was much simpler and less complicated. However, it wasn't as not as precise or able to achieve the same drawings that we were earlier, which is fine. Here is the breakdown of the X and then the Y motors, the theta then the phi motors. As you can see, it did one then the other motor at a time. It didn't do them smoothly at one at the same time. So that way I broke it down into smaller steps. Instead of one big swing from here to here, we did a bunch of small ones. That way it kept a smooth path and was more reliable. You can see the different physical traits here, and you can set the different precision magnitudes as well as the speed of the robot in between each step. Here is the length of each arm, and you can set, and you can see the different Arduino receiving and for the G code. And here is down here the SCARA inverse kinematics calculations here. You can see the theta and the phi, which are to be achieved after receiving the G code, that is to go to. And once you set the motor angle, you have the 2 phi and the 2 theta. And we use the ratio between the number of X steps and number of Y steps required. And say you have 3 times as many X steps as you have Y steps. And so every 3 Y steps, you have 1 extra. That way the ratio remains the same, but it's a smooth transition from here to here by doing a bunch of smaller movements, breaking it up into segments, versus one swoop down and one swoop up. And that is all.
My name is Cade Tillema, and I was in charge of both designing the printed circuit board and in installing the components onto the board. The overall idea for the PCB was to interface between the Arduino Uno and the two stepper motors. Here we have two pictures of the front and back of the board. The board itself was a little over 4 square inches. And the idea for the board was to act as an Arduino shield, so with the header pins, they would insert directly into the Arduino, fitting it on with an electrical and mechanical connection. Now we will take a look at each individual component that went onto the PCB. First, we have the two A4988 drivers. These were the drivers acting between the stepper motors, specifically the Nema 17 stepper motors, and the Arduino. Next, we have the set of 4 male header pins that were soldered onto the PCB and fit right onto the Arduino, and then were routed to the drivers. Next, we have 2 sets of 4 male header pins. This is where each of the stepper motors connected to. Next, we have a 100 microfarad capacitor. The main function of this capacitor was to deal with any spikes in voltage. Now at the bottom, below the capacitor, was 2 header pins for the Arduino power supply that also, as well as the PWM, fit right onto the Arduino itself. Lastly, we have the motor power supply. This is a barrel jack that routed to the 2 drivers. This was 20 volts. Here is our electrical schematic of the PCB. As we can see, here are the PWM connector pins routing to the board. This is for this one. Over here we have for the other driver. We also have the barrel jack up here and the capacitor as well. Here we have the actual layout of the PCB. As far as routings go, between 0.3 millimeters and 0.5 millimeters were used for all of the routings. As we can see, the PWM from the Arduino was routed to the direction and step pins of the drivers. Here we have the power supply for the Arduino down here. And here's the barrel jack that routes to the motor power supply pins on the drivers. And here is our ground plane in the blue. And here is a side-by-side picture of the layout and the actual board. And this is our end result of the PCB fitted onto the Arduino, acting as a CNC shield. Now, I did face one major problem. The fragility of the A4988 drivers caused some issues. Soldering them onto the board actually fried the drivers themselves, and it's very difficult to unsolder them and replace them. Luckily, Oshpark delivered 3 circuit boards, so we were still able to use one of the other ones. And our solution to this problem was, instead of soldering the driver directly onto the board, we would use female header pins. So we would solder the female header pins on, and we would be able to slide the drivers right on in case they were to burn out again. As we can see here, the drivers are fitted onto those female header pins. Now, in conclusion to our 2-axis robotic arm project, we were able to integrate and implement the Python graphical user interface, the e-ink display, the actual mechanical configuration and construction, the coordinated movement, and the PCB Arduino shield to result in our 2-axis robot arm, as you can see here. Thank you very much for watching our presentation. We hope you enjoyed it.